Imagine standing on the edge of the Grand Canyon and realizing that the walls around you contain 2 billion years of Earth's history, layer by layer, like pages of a book. Now imagine flipping through those pages and suddenly finding something that shouldn't be there. Not a fossil, not a crystal, something that looks unmistakably like it was made by someone with intention, with intelligence. That thought kept Adam Frank awake at night. Frank is not a conspiracy theorist. He's an astrophysicist at the University of Rochester, one of the most respected researchers in the field of planetary science. And in 2018, he co-authored a paper that asked one of the most quietly terrifying questions in the history of science. What if we are not the first? What if, hundreds of millions of years before humans ever walked on this planet, another civilization rose, flourished, consumed, and vanished, leaving almost no trace? The paper had a name borrowed from a British science fiction show. They called it the Silurian hypothesis. And once you understand what it actually claims, you will never look at a piece of rock the same way again. Let's start with what we know. Earth is 4.5 billion years old. Complex life has existed here for roughly 600 million years. Homo sapiens, our species, has been around for approximately 300,000 years. Industrial civilization, the kind that burns fossil fuels, builds cities, launches satellites, and fills oceans with plastic, has existed for less than 300 years. 300 years out of 4.5 billion. That is the equivalent of the last 2 seconds of a 24-hour day. A blink, a breath, almost nothing. Now, here's the question Frank and his co-author, Gavin Schmidt, director of the NASA Goddard Institute for Space Studies, dared to ask in a peer-reviewed scientific journal. If another species had done what we are doing, built an industrial civilization, burned through resources, altered the atmosphere, but did it 50 million years ago, or 100 million years ago, or 200 million years ago, would we know? Could we know? Would any trace survive? The answer they reached after careful analysis is both fascinating and deeply unsettling. Probably not. Almost certainly not. And the reasons why will change the way you think about the ground beneath your feet. Let's begin with the most basic problem. Rock does not preserve everything. In fact, rock preserves almost nothing on geological timescales. The oldest surface rocks on Earth are roughly 4 billion years old, but they are vanishingly rare, scattered across Canada and Greenland, like fragments of a broken mirror. Most of the rock you walk on, build on, and dig through is far younger, hundreds of millions of years old at most. And even that rock has been folded, melted, subducted into the mantle, compressed, shattered, and reformed countless times. The geological record is not a library. It is a library that has been repeatedly flooded, burned, and rebuilt from fragments. Most of the books are gone. Think about what that means in practical terms. If a civilization existed on Earth 70 million years ago, around the time the last non-avian dinosaurs were still alive, almost all physical traces of that civilization would be gone, completely. The buildings would have dissolved. The roads would have eroded. The metals would have oxidized and dispersed into the surrounding rock as trace elements indistinguishable from natural deposits. Even stone structures, which we assume are permanent, are not permanent on geological timescales. The pyramids of Egypt are roughly 4,000 years old. They are already eroding. In 10 million years, they would be unrecognizable. In 100 million years, they would be gone entirely, replaced by a thin layer of calcium carbonate in a sedimentary sequence that no future geologist could distinguish from natural limestone. Frank and Schmidt worked through these numbers with painful precision. They asked, what would survive? What markers of industrial activity are robust enough to persist across tens of millions of years of geological processing? The list is shorter than you might hope. Synthetic chemicals, certain plastics, chlorofluorocarbons, industrial byproducts, could theoretically leave molecular signatures in sedimentary layers, but organic molecules degrade. They break apart. They get metabolized by bacteria. A plastic bag buried in sediment might last thousands of years, perhaps tens of thousands, but not hundreds of millions. The chemistry would be unrecognizable. There is one marker, however, that does survive: carbon. Specifically, the ratio of carbon isotopes preserved in ancient rock. When an industrial civilization burns fossil fuels, coal, oil, natural gas, it releases enormous quantities of carbon dioxide into the atmosphere. That carbon has a specific isotopic signature. It is depleted in carbon-13 relative to carbon-12 because fossil fuels are derived from organic matter, which preferentially incorporates the lighter isotope. This isotopic shift gets recorded in the rock. It gets locked into limestone, into ocean sediments, into the shells of tiny marine organisms that sink to the seafloor and become part of the geological record. And it persists for millions, possibly tens of millions of years. Here is the crucial point. We have already found these isotopic anomalies in the ancient rock record. There is a famous event called the Paleocene-Eocene Thermal Maximum, or PETM, which occurred approximately 56 million years ago. In a geologically brief period, perhaps 20,000 years, perhaps less, Earth's temperature spiked by 5 to 8 degrees Celsius. Carbon isotope ratios shifted dramatically. Oceans acidified, species went extinct. Scientists have debated the cause for decades. The leading explanation is a massive release of methane from the seafloor, volcanic activity perhaps, or the destabilization of frozen methane hydrates. But the event is so sudden, so dramatic, and so similar in its chemical signature to what we are doing right now, that Frank and Schmidt used it as a comparison point in their paper. They wrote, in effect, that if an industrial civilization had caused the PETM, the geological signature might look exactly like what we see. We cannot rule it out. That statement, from two of the world's most respected planetary scientists, published in a peer-reviewed journal, is one of the most quietly radical things written in mainstream science in recent decades. They are not claiming there was a pre-human civilization. They are not saying the PETM was caused by industrial activity. What they are saying is something more philosophically troubling. We might not be able to tell the difference. Our instruments, our methods, our entire framework for reading the geological record might be insufficient to detect a civilization that operated at industrial scale 50 million years ago. We have a blind spot, and we don't know how large it is. Now, let's zoom out further. Because the PETM is only 56 million years ago, and complex life has been present on Earth for more than 500 million years. That means there are more than 450 million years of Earth history, filled with complex organisms, stable atmospheres, and liquid oceans, during which we have no particular reason to rule out the emergence of intelligence. We have not found it. But as Frank and Schmidt's analysis shows, absence of evidence is not evidence of absence, not when the geological record is as incomplete and degraded as it is. Consider the Carboniferous period, which lasted from roughly 360 million to 300 million years ago. This was an era of extraordinary biological productivity. Vast forests covered the land, forests so dense and so extensive that when their trees fell, they were not decomposed, because the bacteria and fungi capable of breaking down lignin had not yet evolved. Those trees accumulated layer upon layer, compressed over millions of years into the coal deposits that powered the Industrial Revolution and continue to power much of the modern world. The Carboniferous was a time when life was reshaping the planet on a massive scale. Oxygen levels in the atmosphere reached 35%, compared to 21% today, making possible insects the size of hawks and dragonflies with wingspans of 70 centimeters. It was a world almost unimaginably different from our own. And yet, the basic chemistry of life was the same. DNA, proteins, cells. The raw materials for intelligence were present. The question of whether intelligence actually emerged, and if it did, whether it left any trace we could find, is genuinely open. There is a species that deserves particular attention in this context: dinosaurs. We tend to think of them as giant, slow reptilian creatures lumbering through swamps, the stock imagery of 100 years of popular science. But that picture was shattered in the last few decades by one of the most dramatic revolutions in paleontology. We now know that many dinosaurs were warm-blooded. We know they had complex social behaviors: herding, nesting, parental care. We know some of them had feathers. And we know that one lineage of dinosaurs, the Coelurosaurs, the group that includes Velociraptor and Tyrannosaurus, showed a rapid increase in relative brain size over the last 100 million years of the Cretaceous period. The theropod dinosaurs were getting smarter, fast. Canadian paleontologist Dale Russell published a famous thought experiment in 1982. He took Troodon, a small bipedal theropod from the late Cretaceous with the largest brain-to-body ratio of any known dinosaur, and asked, what if the asteroid hadn't hit? What if the non-avian dinosaurs had survived and continued to evolve? His calculations, based on the observed trajectory of brain size increase, suggested that by today, 66 million years later, a descendant of Troodon might have a brain as large as a modern human's. He called this hypothetical creature the dinosauroid. It was bipedal. It had forward-facing eyes. It had hands capable of manipulation. It looked frankly disturbing, a humanoid reptile that evolution might have built if our particular branch of the mammalian family tree had never gotten its chance. The asteroid reset the game, but it was a close-run thing, and it raises a question that once you ask it, you cannot unask it. How many times in the long history of life on Earth has intelligence come within reach of some lineage and then been extinguished before it could make its mark? Let's talk about what extinction really means. We know of 5 major mass extinction events in Earth's history. The most famous is the end Cretaceous extinction 66 million years ago, when an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula of Mexico and wiped out roughly 75% of all species on Earth. The second most famous is the end Permian extinction, 252 million years ago, which was even more catastrophic. More than 90% of all marine species and approximately 70% of all terrestrial vertebrate species vanished. Geologists call it the Great Dying. It was the closest Earth has ever come to becoming a dead planet. But here is what is less often discussed. We don't fully understand what caused the end Permian extinction. The dominant theory involves massive volcanic eruptions in what is now Siberia, the Siberian traps, which released enormous quantities of carbon dioxide and sulfur dioxide, triggering runaway greenhouse warming, ocean acidification, and widespread anoxia in the seas. It is a plausible and well-supported hypothesis. But the extinction was so sudden, so complete, so catastrophic, that some researchers have wondered whether the volcanic activity alone is sufficient to explain it. The isotopic signature of the end Permian includes exactly the kind of rapid carbon release that we see in human industrial activity. It includes ocean acidification. It includes a die-off of marine calcifiers, the tiny shell-building organisms at the base of the ocean food web. That is eerily reminiscent of what climate models predict for our own future if carbon emissions continue unchecked. Frank and Schmidt, in their Silurian hypothesis paper, noted this explicitly. They pointed out that the geological signature of a civilization that burned through its fossil fuel reserves in a geological instant, say over 5,000 years, which would be invisible in the rock record, would look from the outside like a brief volcanic episode or a bolide impact or some other natural catastrophe. The civilization itself, its cities and roads and technologies, would be gone. What would remain would be a thin chemical smear in the sediment, elevated carbon, altered isotope ratios, perhaps a spike in certain trace metals associated with industrial activity. And then, nothing. The planet would recover as it always does. Life would continue. New species would evolve. And millions of years later, some curious descendant of those new species might look at that thin chemical smear in the rock and see a natural anomaly. A volcanic episode. A mystery, not what it actually was. This is not science fiction. This is a legitimate methodological concern raised by serious scientists, and it connects to a broader question that has haunted the search for extraterrestrial intelligence for decades. The Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" notes that given the age of the universe and the vast number of stars, intelligent civilizations should be common. Yet we see no evidence of them. The usual explanations focus on the distances between stars, the difficulty of interstellar travel, the possibility that civilizations destroy themselves before becoming spacefaring. But the Silurian hypothesis adds a new layer to this paradox. What if civilizations don't need to travel to other stars to become invisible? What if a civilization can rise and fall right here on Earth, anywhere in the universe, and leave almost no record? What if the universe is filled with planets that have hosted intelligence repeatedly without knowing it? Our planet does not give up its secrets easily. It stores them in the language of chemistry and isotopes, in the compressed silence of sedimentary sequences, in the whisper of ancient carbon locked inside stone. Every time we develop a new tool, a more sensitive spectrometer, a deeper drilling capability, a more sophisticated algorithm for detecting geochemical anomalies, we read a few more words of that language. We are only at the beginning of understanding what this planet has been through. We may have companions in the deep past that we have not yet recognized. What do you think? If another civilization existed here before us, where would you look for evidence? What question would you most want answered? Leave your thoughts below. Because the search for our predecessors, real or hypothetical, begins not in the rock, but in the questions we are willing to ask.